and he will talk about polynomial equations related to the Jacobian conjecture.
Okay. So first I want to thank the organizers for inviting me to this session. I will speak on some recent progress in the Jacobian conjecture. So to make progress in the Jacobian conjecture is very difficult, and to measure this progress is more difficult than that, because how you measure it if you don't solve it. So, but we have made some progress. So this is joint work with Juan José Guchone and Jorge Guchone. And the main work was done in 2014 around this time. So I will focus on them, and then recently we made some progress. So first we'll give some classical results on the plain Jacobian conjecture with two variables. Then some systems of equation will be considered. And we'll see a list of smallest possible counterexamples given by Mo. Well, this is started by Mo, but we gave some list. Then I will present the new system of equations and give some examples and applications. And we have a new conjecture based on the results we have. So I hope everyone knows what the Jacobian conjecture is in two variables. So if you have if you have the Jacobian, which is just this mixed sum of partial derivatives of two polynomials in two variables over a field K, if it is a non-zero constant, then the map has a polynomial inverse map. So the converse is trivially true, because if a map has a polynomial inverse map, then the Jacobian of the composition is the product of the Jacobian. So we have an invertible polynomial in two variables, so it has to be a non-zero constant. Okay, so this is the Jacobian conjecture of 1939 from Heller. And these are some classical results from the last millennium. So if it is false, if the Jacobian conjecture is false, then you have a counterexample, which is a pair of polynomials in two variables, such that the Jacobian is 1, and the degree of P and the degree of Q do not divide each other. So this was proved by several authors last century. And we have a second theorem. If it is false, then these counterexamples are what I call subrectangular. Okay, so the support of the polynomials is contained in a rectangle, and the farthest corner is contained in the support. So this example of triangular counterexample. In fact, this is the smallest possible given on the results we have in previous works. So 48 and 64, this is the same smallest possible counterexample found by Mo in 1983 and by Heitman in 1990. So they are triangular, and obviously the degrees do not divide each other. So this is well, if the Jacobian is 1, I call them a Jacobian pair. This is what means to be subrectangular. So we have a corner AB, and then this corner MAB is in the support of P, and the corner NAB is in support of Q. So M is, in this example, this 3, and N is 4. So if we want to discard the possibility of once we have this list of smallest possible counterexamples, we want to know, well, is there a counterexample? And if it is, can we find it? Then we have to take the coefficients of these possible counterexamples, and well, the Jacobian has its most degree 110, and well, if you have these triangular polynomials, you have 6,105 equations, 3,256 variables. Ij are the coefficients of P, BAA, the coefficient of Q. So if you want to solve it, you say, well, it is overdetermined, so it should be easy to compute, but, well, it is not easy. And so these are the coefficients of P, 100 and 1,076 variables. So taking this first approach and trying to compute it is not a good idea. Okay, you have no chance to get something new. So maybe for polynomials of degree 2 or 3 you have some chance, but otherwise no chance. So, well, the first improvement, if you take this subrectangular shapes, and well, this is work we've done before, and there are some talks I gave with these results. I won't go into details here. So one of my students made this web page, and there this web page, and there you can get all these smallest possible corners. Okay, so we'll see on the web page you get this. So the smallest corners is at 412. Okay, and there are 11 corners that are smaller than 42. Okay, so why 42? I don't know. We wanted to go to 125 of the degree of the possible counterexample. So that's why we choose 42. So and each of these small corners, well, this is the smallest corner for 12. We'll ignore this part, and then M and N, the possible M and N corresponding to one corner are in a linear family depending on J. So when J is 0, then we have here 3 and 4. This is the smallest possible counterexample, and we can compute all this with 3 tables, because on each point there can be different families. So there are not just 11 families, but there are 30 families corresponding to this 11 corner. And well, you try to solve all of this, and we have some tricks to do this. So the smallest counterexample, as I told you, is this with J equal to 0, M3, N4. So we got the same example we have considered before. And well, the original system is very big, several thousands of variables and equations, but well, Mo in 1983 makes some change of variables and some other stuff which I don't understand, and he gets to a system of 10 variables. That's what he tells, and then he solves it, and then he shows there's no counterexample at this place. Okay, the same example is computed by Heitman in 1990, and he uses some theory of divisors of these algebraic curves or Riemann-Roch, and reduces the system to one with 15 quadratic equations and 13 variables. Okay, so although Mo is difficult to understand, one understands some things. Heitman is impossible to understand. So I mean, I get the same numbers as him, but I don't know where they come from with his computation. So we have an article where we this first family, okay, for all J, we transform it into a system of differential equations, and then we can solve the we can solve also the smallest case, but some other cases. So, and our method, just to give a flavor of what we do, is the following. We start from this pair, P and Q, then we transform it into some subrectangular. So you see the number of equations is greatly reduced, but we reduced it further. So we have P1, Q1. Well, this is just a flip x with y, with the symmetric polynomials. For some technical reasons, we have to do this. Then we have this P2, Q2, and then we reduce it further. Here we cut the lower part of the support, okay? In the price we have to pay, we have no more polynomials, but we have here a negative exponent of x. And then we continue with this method. This is the first cut. Then we make some symmetric morphism of the plane, and the price we pay, we are again at polynomials, which are much smaller, but the price is the Jacobian is no longer 1, but now it is x. So, and we make it again. Here we cut along this diagonal, we cut the support, and then we get some smaller polynomials, p5, q5. Okay, but the Jacobian is preserved, is x. We continue. We flip it. Now again, by this technical reason, we have to flip it. Then we cut this last polynomial, p6, q6. We cut it. Well, the polynomial, when we flip the Jacobian was x, now it is y or minus y. And we cut again until we get to the origin. Okay, we cut this lower part of the support. We get these polynomials, which now are very small. So in some way, it should be parallel to the work that Mo does, because the numbers coincide with his numbers, but I don't know how it's related. So we have these smaller polynomials, and then we make again a flip and get this P8, Q8, and now there are not that many equations, okay? One point, obviously, we have here the Jacobian is no longer a constant, but this polynomial, and we have 21 variables and can count, and 19 equations if we take the Jacobian. So this can be solved because, well, I don't know if with the straightforward approach of taking these 19 equations with 20 variables, but we have another approach, as I told you, with differential equations on polynomials. So this was the first family, and you saw the table, we had 30 small families. And actually, the other families are not so easy to reduce. Okay, so only for the first family, we could do 2 times this cut. In the other families, we can do only 1 cut. So it doesn't come to such a small system in the other cases. So, as I told you, none of the other families in the table can be reduced as much as 1. And we solved the cases for j0, 1, 2, 3. There's an article about it. But even in the case j equal 4, so where I think the degree of p is 160 and the degree of q is 208, we cannot solve it because the computer, well, it takes too much time. Okay, so when we were trying to look if there are counter examples or not, we came across this new system of polynomial equations. Okay, so the naive approach gives you m plus 1 minus 1 into the combinatorial equations, and these are the number of coefficients of p and q. Okay, this is when you take the triangular polynomials. And we found a new system of polynomial equations, and only m plus 1 minus 2 variables and m plus 1 minus 2 equations. Okay, so the size of the system is linear in m plus n. Okay, this is quadratic order m plus n. So it's a great improvement because now we have a chance to compute it actually, if there is a counterexample or not. So, and moreover, if you solve this system explicitly, then you can tell if there is a counterexample or if at that place there is no counterexample. Okay, so this was done in 2014. So I will explain how we come to the system. The basic idea is we don't take coefficients of polynomials in 2 variables, but only in 1 variable. And then p and q are the polynomials in x and y. We take here a Lorentz series in x to the minus 1, x inverse, and the coefficients now are polynomials in j. So the coefficients of the new system and the variables in the new system take values in k of j. So we kind of reduce 1 variable. Okay, then C is this this polynomial series, and the coefficients of C are polynomials in J, and these are the new variables in our system. Okay? So the degree of C, which is the evaluation 1 of C is 1, degree of F is 2 minus n, so negative. The principal term of F plus, is taken with respect to this 1, 0 grading, should be y, here y. And, well, C is the n roots of P, which is unique. We assume that P is monic in X, and Q also monic. So this is the unique n roots of P. This is C. And Q, well, if you look here, lambda 0 is 1, so we have C to the m. It's a kind of the m roof of C, but you have to add some additional terms and some additional parameters. And then we have F, which is at the point 2 minus n. So, well, if these conditions are satisfied, then PQ is a counterexample to a Jacobian conjecture. So this is the new system. And now one can solve it effectively for small values. Okay? For example, in this case, we have P, this smallest case, we have P and Q. F is here 2 minus n, n is 48, 2 minus n, so F is the support of F is here on the negative side. C is the n roots of P, so it starts here and has somehow the same form. So we have these elements from which we build our system. And now the first condition that we use is C to the n is P. So, but C to the n is something like this, and you have a big negative part. And P is a polynomial, so the support is only here. So, in order to have this equality, all this negative part must vanish. So, and that's where we get the equations. Okay, C to the n at the place minus 1 should be 0. This is the first equation. C to the n minus 2 should be 0. And we take only equations until the place m minus 1. Okay, so in this case to minus 63. So here we get 63 equations for these variables, and m minus 1 equations. And the variables that appear are the negative coefficients of C. Okay, and we have m plus n minus 2 plus 1, m plus n minus 1 variables, and m minus 1 equations. This is a system. And the other equation that we use is this one. Okay, with, for example, here are only 2 lambdas different from 0. And once again, this sum on the right-hand side, we have F, we have some powers of C, and C to the 64, and this should be equal to Q. So once again, we get the equations from the negative part of this side, which should be 0. So this sum of powers of C at the point minus 1 should be 0. This is the first equation. And so we get, well, n minus 2 equations. And then in the last equation, we have here the leading term of F, which we said should be y. So here we have n minus 1 equations. And the variables, well, happen to be the same. We go until C to the minus m plus n minus 2. And so we got as well, the variable C0 is kind of trivial. You can set it to 0 and you get an equivalent system. And so we have a system with m plus n minus 2 equations and m plus n minus 2 variables. So, and the system is solvable. So it's not that bad. Let's see, well, we call the system S of mn. It depends on the lambda i's, and y is the leading term of F. And one of the main results of our work in 2014 is that the system has a finite number of solutions. So the ideal generated by this system of equations is 0-dimensional. Okay? Actually, the main part of the work was to show that the Jacobian of this system is invertible. So it's not only 0-dimensional, but it's actually a radical ideal. which we haven't used yet, but maybe it will be important at some point. So let's see an example. So a smaller example that we can solve actually. So n equal to 4, n equal to 6, and lambda 8 different from 0, and all other lambda i's equal to 0. Okay, so we'll modify C because we don't take the fourth root, but only the square root, so the equation will be of degree 3 only and not of degree 6. So the system is simpler. So in this case, P is C squared, Q is C to the 3, C cubed, plus lambda 8, C minus 1, plus F. And the equations we obtain is, well, C squared to the minus 1 is 0, to the minus 2 until m minus 1, m is 6. So we have 5 equations here. And we have 3 additional equations from the other side. From this, we have 3 equations. Minus 1 is 0. Minus 2, we have here some lambda 8, because this is times the inverse of C, which starts at minus 2. And then we have this last equation. So we get these 8 equations. Okay, and this can be solved by a computer. You see, the first equation is C to the minus 1. We have until C minus 3, C minus 4, minus 6. So we have 7 equations plus C0. We have 8 variables and 8 equations. Okay, the number of equations, the number of variables is the same. And we have a finite number of solutions. And actually, one can solve it. And you get, for P, you get this solution. Okay, P is x, well, it should be of degree 4. And then you get some fractional powers of y, of y. Okay, y to the minus 2/3, y to the 1/3, y to the minus 4/3. So, and this is the support. There are only 4 coefficients different from 0. And there is something similar for Q. Okay, you can get explicitly. This is one solution, but the system has 3 solutions totally, but the 3 solutions have the same support. So there are some 3 roots of unity here in the other solutions. And this is the simplest to write. That's why I wrote this solution down. So you can solve this system actually, and I must say, in 2014 we weren't able to solve it explicitly, so we only have some indications. Now we have made some progress and have some new tools to solve it. Okay, and notice if we take lambda equal to 0, then we get a new system, and the solutions are the same, but with lambda equal to 0. So this is valid for any lambda. Lambda 8 in this case equal to 0. So this term cancels, this cancels, this cancels, this remains, this cancels, this remains. So the only 3 terms that remain in the homogeneous solutions are only these 3 coefficients. Okay? These 3 coefficients. So if we take lambda 8 equal to 0, we have an homogeneous solutions, and the supports are contained in a straight line. And the same for P. For P we get this solution, for Q the solution, and for C, which is the square root of P, we also get some solution that is contained in this straight line. Well, this goes on until infinity. So, and the homogeneous system obviously is very easy to compute, and we computed the solutions for some systems, and there is a result of Zagier that guarantees that there is always a solution. For any m and n, the homogeneous system has always a solution. Okay, that's also part of the work done in 2014. And this is the result based on the result this result, if there is a solution of the system, here when all the lambdas are equal to 0, then the solution is contained in a straight line. Okay, this is a result we got before. Okay, and then the solutions we just saw of this example are what we call subhomogeneous. That means you have homogeneous solutions, and you have additional terms that are below the straight line from the homogeneous solution. Okay? So this is a definition, somehow technical. We can see here. We have a homogeneous solution and a subhomogeneous solution, which is, I think this is the solution we got in the example I showed before. We have the homogeneous solutions, and all the non-zero coefficients are below this straight line. So it could be that these are Laurent polynomials, but they also could be Laurent series. Okay? And well, when we saw this, I thought, well, maybe all solutions are subhomogeneous, and we conjecture all solutions are subhomogeneous, because we had, when the greatest common divisor is 1, this is true, so based on this one result we thought, okay, this is true everywhere, and then, well, I'm sorry, this conjecture is false. So this is a counterexample. M and n is 4 and 6 as before. Lambda 7 is different from 0, and all the lambdas are 0. Then you get the solution. Okay? It looks subhomogeneous, and as I told you, you can have Laurent polynomials or Laurent series. In this case, you get Laurent series. But, well, the homogeneous solution is on this straight line, so this solution is not subhomogeneous. Okay? The system has 7 solutions, and only 3 of them are subhomogeneous. Okay? So, well, that was the end of the story in 2015. We tried another approach to the Jacobian conjecture, but kind of we let go of the Jacobian conjecture because it's difficult to make some progress, and well, we might know. But well, it's not. Well, it's not really the end. Otherwise, I wouldn't stand here and tell you this sad story. So, around 2018, I had a student which is very capable. He was in competition, in programming competition, international competition. So he made also this web page. So he's very good. And he, well, we wanted to have some advantage of all the work we have put into the Jacobian conjecture. So we tried to compute these smallest examples. So this is the list of all possible counterexamples with degree lower than 125. Okay, so these 2 first belong to the first family that we solved in a paper with these differential equations. Okay, and this smallest example was also solved by Moore and by Heitman, as I showed you. And then for the other examples, well, here's some. This is some other argument of multiplicity that eliminates this possible counterexample, and all the other were verified that there is no example using a modified system of these polynomial equations. Okay, you reduce you take the example, you reduce in the same flavor as I did with the smallest example. You reduce it not as much as the small example, but you reduce it very much, and then you take a modified system, so you have a small number of equations and variables. So you take the coefficients of the polynomial in x to be the variables, and actually at that time we didn't solve the system, but we saw some properties of the solutions that said that there can be no counterexample. So that's what we did. I did with this student. So, and then around 22, I have 2 students, one in bachelor and then in master's, and well, I gave them some work in Grobner basis and said, okay, look at these examples and look at the Grobner basis, and I also started to think about the Grobner basis, and then I found a new tool, and the tool is you have to with these systems of equations, you have to use a Grobner basis with respect to a degree reverse lexicographic order, but the degree is not the usual degree, but it is weighted. So C minus 7, in the example we had before, had weight 9, so decrease in weight until C0. The F, which is actually the Y, I think, in the system, is weight 9. Lambda 8 is considered as a variable and has degree 8. And if you take this and the degree in reverse lexicographic order, then we were able to compute actually explicitly the solutions of the system for small numbers, which is something we couldn't do before. At 4 and 6, the computer just crashed. But now with this new system of a new monomial order, which gave us some useful Gröbner buses, we can solve the system. So, and then we got some results. So, well, this is the result I told you. If the greatest common divisor of MNN is 1, then all solutions of the systems are subhomogeneous. That's why we launched that conjecture, what turned out to be false. And we found out if the lambda i's, well, the i's where d is different from 0, are the d is the maximal divisor of MNN divides I, then and if one can compute the solution set explicitly in all cases, which are not that much, then the solutions are subhomogeneous. So now we are able to compute these cases that before we had no chance. Okay, and moreover, another result, the same condition, only lambda i's, which are multiples of d, can be different from 0. And if the number of solutions here is of the full system is equal to the number of solutions of the homogeneous system, then kind of one expects that for each homogeneous solution you get a subhomogeneous solution. I'm quite sure this is true, but we haven't proved it yet. Okay, it's kind of a Hensel lemma or something like that, that you can expand this solution. And then, if this is true, then this should be subhomogeneous because we haven't proved it yet. And actually, we can compute that for these numbers. So I think this all the smallest, here we have all the smallest pair with the sum lower than 20, I think, and the maximal common divisor, the greatest common divisor greater than 1. I think this is all the pairs, and here we can compute the number of solutions, which is much easier than compute explicitly all the system. And, well, so having said this, we say, okay, this gives place to a new conjecture. So under these same conditions, then also all solutions are subhomogeneous. Okay? And, well, this new conjecture implies not quite is a probable consequence. We have this is work in progress. There are some gaps, but a probable consequence is, well, if you have a system coming from a potential counterexamples, then I'm pretty sure it's true in general, and all the small examples in that table I have computed, and it is true that this condition is satisfied. So if one can prove it in general, then this is no longer probable. Then if you have a subhomogeneous solution, then you have fractional powers of j in the solution. And then obviously it cannot be a counterexample, because in the counterexample the coefficients are polynomials in j, not with fractional powers. So hence the plain conjecture, Jacobian conjecture would hold. Okay? How I'm doing with the time? 5 minutes. Okay. So this is the new conjecture that we are working, and these are the papers. These are the 3 earlier papers, and then Rodrigo Jorritiner is my student. We wrote two papers, and this is Heitman and more. Okay? Muchas gracias. So I have still 5 minutes. So this is work in progress. So any help is welcome, especially from computers and algebra side, because I'm not no expert in neural buses, and I lectured 3 times commutative algebra to learn neural buses. So now that's where we made some progress. Okay. No, it's okay. That was the last slide. No help?
Aquí. Sí, entonces me lo pongo en un bolsillo. Ok, perfecto. Vamos probando, probando. Probando, probando. ¿Se escucha?
Tenemos
Claro.
el 6, el en medio es la luz.
Ya.
Izquierda, derecha.
Ya, para adelante, para atrás. Ahí, perfecto. ¿Y se escucha o no? ¿O ya también está prendido? Ah, ¿me están escuchando? Okay. Ah, perfecto. José Yáñez.
El canal de YouTube de
Ah, para dárselo a mi mamá. Okay, thank you very much for the invitation. It's always happy to come back home and give a talk. So, this is a joint work with Joaquin Moraga and Warren Young, the three of us in UCLA. And so I like this talk because the setup is really straightforward. Like, this is the only definition I need to start working out. So take X to be a projective normal variety over the complex numbers. We will definitely use the non-complex numbers, so I cannot get around that, sadly. And we call an endomorphism from X to X. And when I say endomorphism, I want an honest endomorphism, so non-isomorphic endomorphism. And it will be called a polarized endomorphism. Can we move the... That's better. If there exists an ample divisor such that the pullback of H is a multiple of H for some integer greater or equal than 2. Okay? This setup comes from, I think during the 80s, people started asking questions about algebraic dynamics, and the naive problem that one always has is to classify every single thing that can happen, so every single variety that admits an interesting algebraic dynamics and what kind of endomorphism you can have. And of course, after that you realize, okay, maybe we need more structure to start saying some stuff, so that's where the polarized condition came into action. Okay? And for people expert in algebraic dynamics, everything I say today will also hold for the int amplify case, if you're familiar with that. If not, let's say with the definition, which is a bit more straightforward. So there are two sources of examples of polarized endomorphisms. The first one comes from toric varieties. So if you have a toric variety, you can somehow expand on each direction on the lattice by a factor of n, and then the induced toric morphism from the inclusion will be a polarized endomorphism. Okay? For example, if you are in Pn, then it's just taking each coordinate to a power of m. Okay? And will be the first natural source of polarized endomorphism, and the second source of examples are abelian varieties. So if you have an abelian variety, you can add a point m times, and that will be also a polarized endomorphism. Here the ample would be any symmetric ample line band. Okay? And the natural question one can have is, well, what can we say about the geometry of X if it admits one of these, one polarized endomorphism? Okay? Of course, I'm not saying that all polarized endomorphisms are of this shape, of course not. But we want to somehow classify the geometry once X admits one of these polarized endomorphisms. So we have some general results about the geometry of X. So the first thing is that the codival dimension is non-positive. Okay? I haven't been able to track this result. I'm pretty sure it was known before 2017, but this is the first instant that I've seen it written down. Result by Sheng Meng in 2017. Second condition is that if the canonical divisor is Q-Cartier, then X can have at worst log canonical singularities, so that is good news for people working in Barrasian geometry, specifically in the minimal model program. And in fact, polarized endomorphisms have been shown that you can run an MMP that respects the polarized endomorphism. Okay, so it's a interesting thing to study in that point of view. Also, if X has a polarized endomorphism, then it satisfies Bott vanishing, which is a generalization of Kodaira and Nakano vanishing that says that you have vanishing of these cohomology groups, but now for all i's and j, okay, and any B ample. And that is a recent result by Kawakami and Totara. And for example, if X is Fano, then that implies that it's rigid. Okay, so that restricts even more the geometry of what X can have. Okay, but to be fair, I mean, these are nice properties to have, but there are several varieties that have this properties, so we would like to restrict even more the question. And the running conjecture that started again during the 80s and it's been carried throughout these years is that if we have a smooth Fano variety with Picard number 1 that admits one of these polarized endomorphisms, then X must be the projective space, okay? And here I said non-isomorphic surjective because Picard number 1 that forces that it must be polarized. It will be a multiple of the generator of the Picard group, so there's no mystery there. And in some sense, this is probably the hardest instance of this classification, because any non-isomorphic surjective endomorphism will be polarized, so we cannot impose more structure in our endomorphism to draw some conclusion, okay? And throughout the years, people have been studying these things. For example, okay, we saw the examples of toric varieties, which might not be always the projective space if it has higher Picard numbers. So this conjecture has been refined and extended to more general setups. And the beauty of I'm not putting names here. This is more of like a folklore conjecture that's been like trial and error of the condition that we must have to obtain this conjecture. But the beauty is that essentially the conjecture is saying that if you have a polarized endomorphism, then you are built with toric and abelian varieties. Okay, essentially we fix the singularities that it must have. Okay, so we are imposing that it has KLT singularities. Then it will admit polarized. If it admits a polarized endomorphism, then it's a finite quotient of a toric fibration over an abelian variety. Okay. For example, in the smooth case, this fibration is usually obtained by taking the Albanese morphism. Okay. Yeah. Huh? There are counterexamples. Yeah. LC is. And it's very like a cone, you can find a polarized endomorphism on a cone over an elliptic curve, and yeah, so simply that. LC is always the nemesis to beat in this kind of thing. But KLT works well. We don't know it works fine, but there's been progress towards that. So some partial results of this conjecture is first as per usual, we know it for surfaces. And almost all singular surfaces. I think the only remaining cases are log del pezzo of Picard number 1. Okay, and again, Picard number 1 is the hardest situation. That is work by Fujimoto and Nakayama during the early 2000s. There's I think a series of 4 papers where they classify almost everything you can say about polarized endomorphisms. More recent work by Meng, Zhang, and Zhong is the case when X is a smooth Fano threefold that admits a polarized endomorphism, then it must be toric. The good news about this is that it does not rely on classification. Okay, so there is hope to extend the argument, but it still relies on knowing a lot of stuff about Fano threefold. So to extend the argument for fourfolds, we probably need to know a bit more about Fano fourfolds in order to extend the argument. Third situation, if the Calabi-Yau case was also classified, which is a finite quotient of an abelian variety. Okay, and I want to point out this last result, which is good in the sense that it's valid for all dimensions. Okay, so this is the most general we had for all dimensions, that if we have a rationally connected smooth projective, and they really need smoothness here, okay, that admits a polarized endomorphism, and we now impose a bit more structure on the polarized endomorphism. Okay, what kind of structure? We are essentially we are requiring that it does what it does when it's a toric morphism. Okay, so when you have a toric polarized endomorphism, this happens. So now we're imposing that condition, and we want it to be outside this divisor. Then we obtain that X is toric, but not only that, but we obtain that X delta is a toric pair. So this delta was indeed part of the toric boundary. Okay? Yeah. Huh? Smooth, no, but singular I do. Here. Okay, but let me say that here for a second. Okay, so the non-toric example will become. But yeah, so now the main idea is to impose more conditions on the polarized endomorphism in order to get more positive results. Okay, so but in this case the proof is very restricted by requiring smoothness, and well, we want it for a normal projective variety, so singularities should be allowed. So we need another method to prove it, but the idea, I think, is a nice one to tackle this problem, at least partially. Okay. So one example is from an unpublished small note by Collard and Xu, based on an example by Saltman. So take the action of the permutation group on the coordinates of Pn, and there exists some n, which is, I think, the 9th power of a prime number, so it's a really mysterious number, but it works. And you can also find a subgroup of this symmetric group such that the quotient is not rational. Okay? But these endomorphisms that were taking the powers of the coordinates descends to this quotient. Okay? So, well, this cannot be toric because it's not even rational. Okay? So then you obtain a non-toric variety with a polarized endomorphism. Okay? But you have a diagram of this shape. Okay? So even though this one is definitely not toric, it has a polarized endomorphism, but it's a finite quotient of something that was toric. Okay? So we're still, it's not a counterexample, it's just it's an example that shows that the quotient is required for this conjecture. Okay? So if you introduce singularities, you definitely also need to introduce quotient. Yes? Oh, here is just the hyperplane. Yeah, no, take the hyperplane coordinates. Yeah, like very much toric pair. Yeah, and here you just take the quotient. Okay, and this descent is even stronger because this one also respects this divisor. Okay, so it also satisfies this. But once you lose the smoothness, you cannot recover, it's not toric anymore. But it's a finite quotient of toric, which is fair enough. Okay? So, okay. So, we will be working on the language of pairs now, okay? Because keeping track of a divisor for which this endomorphism behaves well was worthwhile already. So we will say that the endomorphism is a polarized endomorphism of the pair, if it's polarized, of course, but also we want this equality. Okay? So, for example, in the previous, this one and this one satisfy this condition. Okay? So both here, Fm and Gm are polarized endomorphism of pairs. Okay? Of course, we're not aiming to prove the whole conjecture, but with this setup, we're hoping to extract like positive results. Okay, and indeed we did. Okay, so the first result is if you impose that X is of Fano type. Okay, if you don't like the type part, just assume Fano. That's fine. And now take divisor delta that makes Kx plus delta linear equivalent to 0. So this should be called a 1 complement of X. And if this pair admits a polarized endomorphism, then it's a finite quotient of a local Abelian toric pair. Okay, meaning that, okay, we have our pair here, we have a toric variety with the toric boundary, and we have a finite quotient between them. Okay? And how much time do I have? Probably, hopefully a lot, indeed. Because, okay, this is one of the results, but the main, I think the interesting part is how the proof goes. Okay, so I will aim now to give you at least a sketch of the steps we did to prove it. So the first step is what happens if f is Galois, okay? So f is a finite morphism, so now we're imposing extra that f is Galois, so f can be seen as being obtained by the quotient by a subgroup of the automorphism group of this pair. Okay, so we have a diagram of this shape. And a result by who on 2018, I think, proves that, and I think this was known before in specific cases, but that's a more general setup, that the automorphism group of a local ideal pair can be written as a finite extension of an algebraic torus. Okay? Of course, we're not saying here that it must have full rank. If it does, then it's toric, but a priori this could have like very low rank. But still, at least it gives us some nice structure for the automorphism group. And what we prove is that, first of all, the group that obtains this diagram is inside the algebraic torus, okay? And sadly, this proof is brute force group theory, so there's like, we couldn't find a nice proof for it, so it's just diagrams of groups. But it ended up staying inside of the algebraic torus. But more interesting was to prove that in that case, the algebraic torus must have a full rank, okay? So in particular, this would prove that X is a toric variety. And the argument here is that if it wasn't of full rank, then by quotient, taking the quotient by G would have a subvariety of codimension of large codimension that is fixed under reaction. So if I take quotient, I will create singularities, and if I keep taking the quotient more and more, it will get worse and worse singularities, but at the same time, this quotient and quotienting by any power of G is isomorphic to X, so X cannot have infinitely worse singularities. Okay, so that is more or less the argument how to prove that it has full rank. Yeah. Yeah. The delta is effective. Yeah. Yeah.
More than effective. Non-zero.
Yes, indeed. Yeah. But well, we're not assuming it, but we can prove that it must be non-zero. So if this diagram occurs, then delta must be non-zero. A priori, we cannot put that condition, but yeah, indeed, it is true. Okay? So that is the first step. So if we reach the Galois case, then we won. Okay? Then it's even stronger, like we have a toric pair. So the second thing that we needed to do was to learn how to lift polarized endomorphism when we take finite covers of X. Okay? And so we want some, we can obtain a diagram like this by taking fiber products. So here is like no mystery. But of course, you should put some conditions on the finite cover. You cannot expect to take any finite cover and obtain something nice up here. And essentially is taking that is étal outside the divisor delta and the singular locus of X. Okay? Once you impose that, well, you have this nice diagram, and essentially what you're doing here is controlling the ramification of this cover. Okay? So it's not only a lifting of X, but also of the endomorphism of the pair. Okay? So it respects the pair structure. Okay? But of course, if you take the fiber product, Y1 might not be Y at all. Okay? So we want eventually that this thing becomes isomorphic to Y in order to be an honest endomorphism. And the idea is that by maybe not taking F, but a large power of F, then these covers will eventually repeat. Okay? So there will be extensions of coverings of this, and you need to assume some irreducibility. There's some trickiness there, but eventually you get that Yn is indeed isomorphic to Y, and not only that, but is isomorphic as a cover. Okay? So then, okay, maybe you cannot lift f, but you can lift a large enough power of f. But the good thing is that if x has a polarized endomorphism, then you can find a large power such that y now has a polarized endomorphism. Okay? And to check that it's polarized, you just follow the diagram. Okay? That is the nicest part of this work. Okay? So if we have this condition, then we can lift maybe not f, but a large power of f. And the final step is to find a finite cover of x such that the lift of f is Galois. Okay? And the idea for that is to prove that the algebraic fundamental group of this open set U has a normal abelian subgroup N of finite index. Okay? Then that will be a quotient and a nice covering. Okay? This is also saying that this group is virtually abelian. Okay? And the trick for doing this, it was to use results of finiteness of orbifold fundamental groups that we used to replace the finite quotients of here to compute the profinite completion of this fundamental group, plus the Jordan property of those groups. Okay, so essentially what does the Jordan property say is that you have all these groups are virtually abelian, but it also fixes the bounds, the index, only depending on the dimension of x. Okay, so you can go as wide as you want, and it cannot be too small. Okay, and that allows you to pass to a large abelian subgroup in the profinite completion. Okay, so this is a result, I think, in two articles, one by Brown and the other one by Brown, Filipazzi, Moraga, and Sbaldi. The point here is that we needed Fano, so that is also a restriction why we needed the Fano condition. And finally, we'll take the covering associated to this large abelian subgroup, and then you have that is this G is etal over this open subset, and even more because now the algebraic fundamental group here will be abelian, then this map will be Galois automatically. Okay? So then you obtained, so this one is taking a quotient, and this one is toric. Okay? So then you obtain the conjecture in this setup. Okay? Questions so far with this? Yeah. No, y does not need to be smooth. If it's Galois, it's already a toric pair. Yeah. Yeah. Well, if you want to smooth after that, you can maybe go higher, but over here is already good. Yeah. Okay, so we got the result in this setup imposing the condition of Fano. So the next step, of course, was, okay, can we drop the Fano condition? Okay? And that is what we did next. Okay? And when dropping the Fano condition, we also realized that we can be a bit more precise on the kind of singularities that we can allow on X. Okay? So this is what we introduce as partially DLT singularities. So if you're not a friend of the MMP setup, don't worry, keep thinking of KLT and everything will be fine. If not, you can think of DLT, which is essentially you want delta to have simple normal crossing, and that if your log resolution extracts divisor with coefficient 1, then the center of those divisors lie over delta, and PDLT is that those divisors lie on the reduced part of delta. Okay? That's all I will say about PDLT, but just think of KLT or quotient singularity if you might. Okay, so we're dropping the Fano condition. We're imposing now that it has this kind of singularities, and we're assuming also, of course, that it has a polarized endomorphism. Then we obtain that X delta is indeed a finite quotient of a toric local via vibration over an abelian variety. Okay, so we have our pair here, we have a finite quotient, and we have this fibration over abelian variety, and the general fiber we want it to be toric, but not only that, the boundary restricts to the toric boundary on each fiber. Okay? The proof for this one is more or less repeat the ideas from the previous one, so I won't go through the details. Of course, it requires more work. So the first step is to use some result by Yoshikawa that gives us at least a fibration with phenotype fibers. Then we can use our previous result. We have phenotype, we can make it into toric, but now it needs to behave well in the fibration, so now we need to study how this quotient behave in a bounded family of quotients, okay? Now, I said a lot of words, maybe nonsense, but essentially is the same strategy works, but we needed to put more details and work in order for it to work. But the like that I like more of this second set of results is that, okay, now we have our setup, okay, so we have a KLT type variety, local labial pair, that admits a polarized endomorphism, but now we're not imposing that it has a PDLT singularity, okay, so we are, it might be worse than PDLT, okay? Then in that case, there are examples that cannot be made into a finite quotient of fibration, toric fibration over abelian, okay? That doesn't imply that the conjecture is wrong, because X still can be a finite quotient of toric fibration over abelian. But what we prove is that, well, I mean, this one might not be a finite quotient, but we can lift it to a PDLT modification, meaning that we can find a birational morphism from Y to X, making Y this pair PDLT, and now this one will have a polarized endomorphism, so now we can go back to the previous result. Okay? And once again, this one is no longer a finite quotient. Okay? So now this one is a birational morphism, but still we were able to lift everything. How long do I have? 13 minutes. Okay, we'll make this quick then. So, okay, let me see how I explain this part. This part got a bit tricky, but also introduced, I think, really nice ideas. Okay, so we're assuming that X delta is no longer PDLT, so it does not have the kind of singularities that we wanted in order for our previous result to work. Okay, so essentially that means that there is some subvariety over which we extract divisor with coefficient 1. That is not where we wanted them to be. Okay, that is essentially what the condition for PDLT was. We want subvarieties that are centers of divisors that appear with coefficient 1 on a log resolution to be contained on the reduced part of delta. So Z in this case is not there. Okay, so it's a bad log canonical center that we call. Okay, so what we first prove is that over this subvariety we can extract one divisor, one special divisor, okay, such that if we take fiber product and maybe normalization if needed in order for everything to work, over here this one also only extracts E, okay? And the way of proving it was to study the what is called the dual complex of the pair, okay? So with people not familiar with that, think of it as a higher dimensional generalization of dual graph of curves on a surface, okay? But now, if your divisor have more intersection, then you start introducing some simplex of higher dimension simplex that glue all those vertices that correspond to divisors. And what we study even more, so that is a well-known object, although recently it has appeared in more and more articles as a good tool to study this thing because it's related with valuations over the log canonical centers. We study how does the F acts on this dual complex, okay? And what we prove is that F induces a bijection on this dual complex, so it's somehow a dynamic on the dual complex, and not even more. It's if you only restrict your sight over one of these bad subvarieties, then it's collapsible. Okay, so you have a bijection, it's collapsible, so it has a fixed point. Okay, by topological reasons, and that fixed point corresponds to this divisor. Okay, so that is how we obtain this special divisor. Okay. Once again, this y1 might by all means not be isomorphic to y. And here I'm secretly replacing f with a large power, right? Because z might not be sent to z, but well, a higher power should do that, okay? Because it must send log canonical to log canonical centers, okay? So, but again, we have this problem, y1 might not be y. So we need to build an argument so that, okay, take a higher power of this and do the same diagram, and eventually it repeats. Okay, that is what we did in the previous setup. Now we need to do more or less the same thing. Of course, here we have like less thing, like I don't know, why would this ever repeat? And the argument we came up with is that, okay, for each n, take this diagram, okay, built in the same way as this, like fiber product and normalization. And over this y and yn, take a small q factorialization, okay? We're not assuming that these are q factorial, but we can find a small birational morphism that makes this small q factorial. And the beauty is that now this minus e is ample over x, okay? So in that setup, we can say that this map is a relative Morey-Green space, okay? And Morey-Green space are nice enough morphism. So in particular, we'll have finally many small q factorial models, okay? Meaning, okay, this is a small q factorial, this is q factorial, and this is a small q factorial model of this one, okay? There are only finally many, so, well, take a really large power of n, and eventually they will repeat, okay? So by using the finiteness of small q factorial models, we can we can restrict our sight only to powers that make this that take the same small q factorial modification here, okay? But of course that doesn't tell me that this one is, that these intermediate things are equal, okay? It only tells me that up here they are the same thing, okay? So now we restrict our sight only to those powers that make this top level of the diagram equal, okay? But we still have relatively Morey-Green space vertically. So they do not only have finally many small q factorial modification, they also have finally many contractions, or in this case, contractions over x, okay? Well, I start from here and I start contracting things, and I will start obtaining these kind of things. These are birational morphisms, okay? So they are obtained by contracting, by making contractions starting from y prime. Well, I have only finally many intermediate contractions. I can take n as large as I want, so eventually they will repeat, okay? Here I'm kind of cheating, maybe y is not the repeated one, maybe it's like, I don't know, y2 and then y15, whatever, but there will be a repetition over which then we can leave the polarized endomorphism, okay? And you do this for one such bad subvariety, where this didn't work, but now we're extracting a divisor, z might up there might still be bad, but now it's contained on the reduced part of the boundary. So we reduce the, this one is a bit more PDLT than this one, okay? And you can only have finally many of those bad subvarieties. So eventually if you keep repeating this inductively, you will get rid of all of them, okay? And then you obtain this diagram where, okay, you need to take a really high power of f maybe. We did like 3 replacement in the meantime. but you will find this birational morphism that makes this one PDLT, and now you should be complaining, okay, how do I know that this one is polarized endomorphism? I mean, it's a nice morphism, but it might not be polarized. And at first I was also scared because, let me go back real quick. Here you use the fact that pullback by finite morphism is still ample, okay? But here you have a birational thing, so pullback might not be ample anymore, and so you cannot use the same diagram to keep track of it. Good news is that many people have studied also some structure on this polarized endomorphism, and they told us, hey, it is enough to check it for big and F. So okay, I say, okay, I have an ample here, I can pull it back to big and F, still follow the diagram, and the story repeats as the previous one, replacing ample with big, and I think you only need big, not even F. So replace with big, and you can still keep track of knowing that if this one is polarized, then this one must be also polarized. And I think that's all I have to say, so thank you. Yeah.
Do you prove that it's only a toric vibration, or can you prove that it's actually a compactification of a Sinovidian variety or something?
So what we prove is that so we prove a bit more than only toric vibration, that is locally a product. Yeah, but no, what you say, I don't know if we can.
It's also the natural example of the sphinx in the local context are these, right? You take this quasi-abelian or semi-abelian variety, and then you take endomorphism composed with translation, endomorphism of the group structure.
Right.
And they extend to, but I was wondering if this power of F would have such a structure or not.
No, that I wouldn't know. Yeah. But yeah, no, I no idea, to be fair.
Any further questions?
Yeah. Yeah. And in fact, we constructed examples to make all the statement as sharp as possible. So yeah, like no finite cover becomes toric, or no resolution becomes polarized, stuff like that. We cover all the possible bases, and with not too complicated examples, just like taking P1 or P2 with some interesting boundary, and that usually settles. And maybe a quotient here and there, but yeah. Huh? That I wouldn't know. That I know that the irrational, like in Solomon, they prove that is rational. This article is devoted to create examples with terminal singularities and polarized endomorphism. It was somehow a way of saying, hey, careful with the singularities, you might need a quotient. And they, in fact, like they refer to this paper that is more or less like algebraic instead of geometric, and yeah, in there, and the group is quite mysterious, so I honestly cannot follow like what is actually happening there, but yeah, like in that paper, it's from the 80s, they give an argument for the irrationality.
Further questions or comments? Well, we resume in 11 minutes.
Okay.
Let's thank you.
tengo una visita si desea ponerlo en alguna parte. Hay que encender el botón de ahí que está aquí.
Ah, ok. Solo cuando empiezo, ¿no? ¿Sí? Ya empiezo, ya.
Enciéndelo nomás porque... Ahí. Ahora. Ahí queda encendido. Y en medio el láser.
Ok.
Izquierda y derecha se mueve. Si usted quiere...
Ok. Deixa eu pegar um relógio. Si tengo tiempo, al final me gustaría hacer una cosa en la pizarra. Okay.
Well, let's talk of the algebraic geometry session. I have the pleasure to introduce my colleague, Sonita Carolina Araújo, who will speak about problem of exactness.
Thank you, Jorge. So first of all, I'd like to thank Jorge and Giancarlo for the invitation. It's a pleasure to be here, and I would like to apologize for missing most of the talks of the session. We just arrived this morning. But anyway, today I want to tell you a little bit about a problem that is attributed to Giza tooling. So let me start. So these are the two papers that whose results I'm going to cover in this talk. So the first one is a joint work with Alacio Corte and Alex Massarenti. It's already in the archive since last year. And then a second one with Daniela Paiva and Socrates Zicas, which hopefully is going to be coming soon. And before I forget, let me say that I will always be working over the complex numbers. Okay, so let me start with some motivation to Giza tooling's problem. So this is automorphisms of smooth hypersurfaces. So this is so I take X as smooth hypersurface of degree D in projective space. And there's this classical theorem by Matsumura and Monsky that says that except in two exceptional cases, namely a cubic curve in P2 and a quartic surface in P3, the automorphism group of the automorphism group of the hypersurface, all the automorphism groups come from automorphisms of the projective automorphisms of the ambient space. So let's look at the two exceptional cases. So the first one is a cubic curve, so a genus 1 curve. So in this case, the automorphism group of an elliptic curve is very well known. So there is the C acting on itself as by translations, and then some finite part of length D, where D is 2, 4, or 6. So this is very well known. So in this case, of course, the automorphisms that come from automorphisms of P2 are only finitely many. So most of the automorphisms of the curve, of the elliptic curve, they do not come from the ambient P2. Now, from the case, the other exceptional case, the case of a quartic surface, so this is a K3 surface. Well, here, the automorphism is, it's always discrete, the automorphism group of the K3 surface. And well, then it depends. We will see some examples. It may be finite, but in many cases, it is infinite. And in all these cases, the subgroup of the automorphism group of those coming from the ambient space forms a finite subgroup. So most in this, so the question is, where do the other automorphisms come from? So let's look at the first exceptional case, the case of a genus 1 curve. So here, well, it's well known. It's not difficult to prove that every automorphism of the cubic curve, well, not induced by an automorphism of P2, but it's still induced by a Cremona transformation of P2. And this is actually not difficult to see. What you have to do is you have to write down C in its Weierstrass normal form, and then you write the expression for the translation by an element of the curve. And when you write this expression, you immediately see that this actually defines, this expression defines a Cremona transformation of P2 that then restricts to the given translation. So this is easy to see. And then, so let me introduce some characters here. So we have, so in the middle is what we call the decomposition group of the cubic. So these are exactly the group of Cremona transformations of P2 that stabilize the curve C. And then, so what we're saying, what this first statement says, that it surjects onto the automorphism group of the curve. And when you look at the kernel is classically called the inertia group of the cubic. So this is the group of Cremona transformations that restrict to an identity on the curve C. So these two groups have been very much studied. So Ivan Pan in 2007 gave generators for the decomposition group, explicit generators. And then in 2008, Jeremy Blanc described generators for the inertia group. So the first example, the first exception is well understood. And now let's look at the second exception, which is the case of K3 surface. So I have now a smooth quartic surface in P3. And so this is the problem of Giza-Tooling that I want to discuss. So so the question, so I learned this in a paper of Ogiso, where he attributes to Giza-Tooling, even though I don't think I ever found it explicitly stated anywhere in any of Giza-Tooling's papers. So he asks, is every automorphism of the quartic surface induced by a Cremona transformation of the ambient space? And so this is the question that I want, that is sort of motivates this works. And well, so I will come back to this question in the end, and then maybe give some answers. But let me just first make some remarks. So this is very well known that if you have a smooth quartic surface in P3, its Picard number is between 1 and 20. And the most, if you take a very general quartic surface, it will have Picard rank 1. And if it has Picard rank 1, then the automorphism group is trivial. So in this case, the question is not really interesting. But when you increase the Picard number, then you get more automorphisms, and then this question really becomes meaningful. So for instance, if you take a quartic surface with Picard rank 2 and take it, say, general in its moduli space, then these are the possibilities for the automorphism group of the quartic. And it's either trivial, or it's a cyclic of order 2, or it is Z, or it is a free product of two copies of Z2. So these are the possibilities, and see, especially in this infinite dimensional cases, that the question become very meaningful. So the first, so as I said, for Picard rank 1 is not interested, so let's consider the higher Picard rank cases. So there have been some examples of positive and negative examples for this problem. So the first example that was studied by Ogiso, so this was the first negative example, was given by Ogiso. He constructed a quartic surface of Picard rank 2, for which the automorphism group is Z, and no non-trivial automorphism of S is induced by a Cremona transformation. So the answer is no. However, he shortly after he wrote another paper where he constructed a quartic surface of Picard rank 3, for which the automorphism group is it's a free product of 3 copies of Z2. So it's much more complicated group. And however, for this example, every automorphism of S is induced by a Cremona transformation of P3. So at this point, he even raised the question of, is it true that every automorphisms of finite order is induced by a Cremona transformation? And then, well, more recently, there has been a counterexample to this question by Paiva and Quedo. They constructed a quartic surface with Picard rank 2 with automorphism group Z2, a free product Z2. And in this case, again, no non-trivial automorphism is induced by a Cremona transformation. So these are some examples and non-examples. And what I want to do today is to explain a tool that we have been developing to study this problem in a systematic way. So let me first introduce what are the tools that were used in these examples and the new tools that we introduced. So the first tool that is very much used is the tool of is the theory of lattices and K3 surfaces. So here, if you have an automorphism of a K3 surface, it will induce an isometry of the Picard lattice. And the global Torelli theorem says exactly that this correspondence is injective. So one can use the symmetries, the isometries of the Picard lattice to understand the automorphism of the K3 surface. So this is one of the ingredients. And another one that was used in the negative examples is some tools coming from birational geometry and the Sarkisov program. And now, in order to study the problem in a more systematic way, and as we will see, for instance, we will be able to solve the problem for Picard rank 2, we have to use a more refined tools. And this is what I want to explain today. The tool that we've been exploiting comes from the fact that this pair of P3 together with a quartic surface is an example of a Calabi-Yau pair. So S is an anticanonical divisor in P3. So if you study the geometry of Calabi-Yau pairs, the birational geometry of Calabi-Yau pairs, and in particular, there is a version of the Sarkisov program for Calabi-Yau pairs, which is what we call the volume-preserving Sarkisov program. You get much more information, and as we will see, this will allow us to say much more about this Gizatuling problem. Okay, so let me now start by properly introduce the Calabi-Yau pairs. So Calabi-Yau pair is a pair, X, D, where X is a projective variety with terminal singularities. If you don't know much about the singularities of the MMP, you can think of a smooth variety. D is, as I said, it's an anticanonical hypersurface. So it's a hypersurface that is linear equivalent to minus K. And we also impose some restrictions on the singularities of the pair X, D. So we ask that it's log canonical. Again, you can think of this as a smooth, say a smooth variety and a smooth hypersurface. That will do for the moment. So, for instance, we can take P3 with a surface with a smooth quartic surface, or even I can even allow for some singularities in the quartic surface. This is an example of a Calabi-Yau pair. And now in this we'll introduce a category of Calabi-Yau pairs. I want to define what is a morphism in this category. And so I want to define the notion of a volume preserving map between two Calabi-Yau pairs. So if I have any birational map between, so I take fixed two Calabi-Yau pairs, x dx and y dy, and I say that a birational map between x and y is volume preserving if the following condition holds. So if for any log resolution of the map, so I take W, say a smooth variety that resolves this birational map, and for every divisor on W, if I compute the discrepancies of this divisor with respect to the two pairs, they are the same. So this is a very, for a birational geometry, this is a very natural notion to consider. Okay, so let me explain why do we call this volume preserving, this terminology. So this is the useful definition. This is the definition that we actually check in practice to see if a map is volume preserving or not. But let me give you an equivalent definition that explains this terminology. So if I take a Calabi-Yau pair, to say that D is an anti-canonical divisor is exactly saying that there is a volume form, a rational volume for omega D that is unique up to scaling, whose divisor is precisely minus D. And now, if I have a birational map, it will induce an identification between the volume forms, the rational volume forms on X and Y, and it is volume preserving. This map is a volume preserving map for these pairs, if and only if this identification identifies the two volume forms. So this is why this terminology. Okay, so now that we know it as a volume preserving map, I can define the birational group of a Calabi-Yau pair. The birational group of a Calabi-Yau pair is the group of birational self-maps of X that are volume preserving for this pair. And so this is this group, as I will explain soon, we have lots of tools from birational geometry to study this group. But now, why is this useful for Giza-Tunning's problem? And this is for the following remark. So the decomposition group that we have seen before, the decomposition group of a pair can be defined as the subgroup of the group of birational self-maps of X that stabilize D. So this is the decomposition group of the pair. And they are, in the case when the pair is canonical, so the singularities are even milder than log canonical, then these two groups coincide. And then the good thing is that for the first one, for the birational group of the Calabi-Yau pair, the group of volume-preserving self-maps of a Calabi-Yau pair, we have some very nice tools coming from birational geometry that we can then apply to study the decomposition group. So, for instance, this is the case when X is P3 and the divisor D is a quartic surface and doesn't even have to be smooth. I can allow it to have at worst rational double points, and this will still be a canonical pair. And then we can use birational geometry to study the decomposition group. So now what I want to do next is to explain the tools that we have from birational geometry to study the birational group of a Calabi-Yau pair. Any questions so far? Okay, so now let me, this is just a remark to say that the canonicity in this remark is actually necessary. So there's this very simple example. If I take X to be P2 and the divisor D to be the union of the three coordinate lines, the triangle. If I take this, well, I'm taking an affine representation for the volume form. In affine coordinates X, Y, I take this form. So this is precisely so this was the divisor in this case is the union of the three lines. If I take the standard, if they take the standard Cremona transformation, it clearly preserves that form. And so it is volume preserving, but of course it is not a birational map when I restrict it to the divisor. So the canonicity is really necessary so that we have the decomposition group equal to the group of birational transformations of the pair. Okay, so now I go to birational geometry, and before I introduce these tools that are specific for Calabi-Yau pairs, let me review some more classical theory about the Cremona group. So the Cremona group of Pn is the group of birational self-maps of Pn. And this is a huge group. In the case, so this is an example of a birational self-map of P2, the standard Cremona transformation that we saw before. In dimension 2, there is this classical theorem by Neder and Castelnuovo that says that the Cremona transformation, the Cremona group of P2, is generated by the automorphisms of P2 and this one standard quadratic transformation. So this is a very, very, very nice result that certainly does not extend to higher dimensions. So in dimension at least 3, there's this well-known theorem of Hilda Hudson that says that if as soon as the dimension is at least 3, the Cremona group cannot be generated by elements of bounded degree. So it's very different than the two-dimensional case. So in the two-dimensional case, we have automorphism, which have degree 1. These are just linear maps. And we have the standard quadratic transformation that has degree 2, and they generate everything. So this is certainly not true in higher dimensions. And in fact, there are no known explicit set of generators for the Cremona group. However, we still have a sort of a weak factorization theorem, which is what we call the Sarkisov program. So what the Sarkisov program, so this was proved in dimension 3 by Corti, and in arbitrary dimension by Hake and McKernan, using tools from the minimal model program. It says that if you have a birational self-map of Pn, it can be decomposed into as a composition of simple birational maps. Well, there is one subtlety that when you take this decomposition, the intermediate maps are not necessarily from Pn to Pn. So the intermediate varieties are now Mori fiber spaces. So Mori fiber spaces, let me just recall the definition. So they come again from the minimal model program. So these are Xi is a terminal projective variety with terminal normal projective variety with terminal singularities. This morphism has relative Picard rank 1, and the anti-canonical of X is relatively ample. So these are the outcomes of the minimal model program when we apply them to a uni-ruled variety, or more in this case, we are interested in rational varieties. So these are the intermediate varieties, and the simple maps that appear in the decomposition are what we call elementary links, and they're called elementary links because they are the most elementary maps between these Mori fiber spaces. So instead of giving the general definition, let me first review what the surface case, and then maybe this is a good example to keep in mind. So in the dimension 2, the Mori fiber spaces are only of 2 types. So either you have P2 and mapping to a point, or you have a Hirzebruch surface with its P1 bundle structure to P1. So I call it Fm. So the F0 is P1 cross P1. F1 is the blow up of P2 at the point, and so on. And now let me define the elementary links in this setting. So there are 4 types of elementary links. So the first one is just you start with P2, you blow up a point, and then you get a F1 with a P1 bundle structure to P1. So these are now the Mori fiber spaces, and the blow up is the elementary link. So this is a very simple one. Another one is if you have a Hirzebruch surface, you can blow up one point. I call this blow up Z. And then I can blow down the strict transform of the fiber through this point. Then I get to F, well, plus or minus 1, depending on whether I chose the point on the negative section or not. And then, so this is the link of type 2. The link of type 3 is just the inverse of a link of type 1. And then a link of type 4 is just, well, in the case of a P1 cross P1, you can think of the map as being the identity, but then I change the fibration. I take a different projection. So these are the 4 links in the 2-dimensional case. And in higher dimensions, I have 4 types of links, and they are very similar to the surface case. They're just a little bit more complicated. So let me explain 2 of them. So the first, the type 1, in the higher dimensions, what I do, I take F to be a divisorial extraction, or you can think of this as some blow up, or something a little bit more general than a blow up, but again, it maps a divisor to a higher codimension variety. Then I get Z. That Z may not have a fibration, but I may have to do some small modification so that phi is a composition of flips, flops, and anti-flips, and then I get a Mori fiber space structure. So this is the link of type 1 in higher dimensions. Same thing for the link of type 2. Again, I can blow up some subvariety of X, or more generally do a divisorial extraction, maybe do some flips, flops, anti-flips, and then again contract the divisor and then get to another Mori fiber space. So this is the second type of link, and then again the other ones I generalize in a similar way. Okay, now I go back to the setting of Calabi-Yau pairs. So as I said, then those elementary links allow us to decompose maps, birational maps of Pn. So now if you have a map now between a Mori fiber space, a Calabi-Yau pair, say P3, comma, a quartic surface, you want to decompose it as a composition of simple links, and then we have a volume-preserving Sarkisov program. So it says that any volume-preserving birational map between Mori fiber Calabi-Yau pairs is a composition of a volume-preserving Sarkisov link. So what it means is that, again, you can think of this as, say, a P3 and a quartic mapping to a point. So if I have a map, but it's a bit more general, but if I have this map, I can decompose it, and then it's exactly like the Sarkisov program, but in every step, I have a divisor D and a Calabi-Yau pair, and all these links are volume preserving. So let me just show you in a picture. So there's no difference between the type of links. The only difference is that I have a little bit more structure. So not only I have the variety, say here, X, Z, and X prime, but I have a divisor in each of them, such that each pair is a Calabi-Yau pair, and each birational map is a volume-preserving birational map. Now, why this? Now, this makes things much more rigid. So let me just give you one example. This actually it's an easy exercise. If you have, say, you start with a smooth hypersurface of degree n+1 in Pn. So this gives you a Calabi-Yau pair, and now take some blow up. So F from X to Pn is a blow up along a smooth center. And then I want to know, and suppose that it's volume preserving, then the center cannot be anything. In fact, the center of the blow up must be contained in D, and it must have codimension 2 in Pn. So before I could blow up any subvariety of Pn to construct a link. And now, if I want to take a volume-preserving link, I have to blow up a subvariety satisfying these properties. And as we will see, this will impose lots of restrictions, and this will allow us to understand birational maps of birational groups of Calabi-Yau pairs. So let me now explain how we can use this tool, say, to prove some results. So that's let me prove to you the following result. Suppose that you have a quartic surface, a very general quartic surface in P3. So I have already told you, if I take it very general, then the Picard number is going to be 1, and then there is no automorphism, non-trivial automorphism on S. But now we are going to prove even more. We are going to prove that the composition group of this quartic surface is trivial. So you could still, in principle, have some Cremona transformation of P3 that would restrict to an identity on X. But we will see that this is not possible. And here, when I say very general, I mean that S is smooth, and the Picard rank is generated by the restriction of a hyperplane section. So now let's see how we prove this. So suppose that we have a non-trivial birational self-map of P3 that restricts to an automorphism that preserves the surface S. Then we can take a Sarkisov factorization, and now let's look at this first link that appears in this factorization. So by my previous example, well, this first link that usually it would start with some divisorial extraction or some blow up of something in P3, but then because everything has to be volume preserving, I cannot just blow up anything. I have to blow up a curve contained in S. Now, so I have to start by blowing up a curve contained in S. But now, if I use my second assumption here, that the Picard group is generated by the restriction of a hyperplane section, we can see that this curve that I will have to blow up is going to be a complete intersection of S with some other surface. And then this is enough for you to actually write down very explicitly what this map is. So you check that this other surface that cuts this curve must have a degree smaller than 4. So it's either 1, 2, or 3. And then in the end, when I come back to x1, so I blow up, and then maybe I have to do some flips, flops, anti-flips, but then I have to contract this strict transform of this other surface that cuts C. And then it's very easy, a simple computation to show that this will have worse than terminal singularities, which is not allowed by the Sarkisian program. So this is impossible. So this shows that you cannot have an element in this decomposition group. So this proves this theorem. And so this also shows that if you want to construct interesting decomposition groups of quartics, you have to take a spatial quartic. And then here there are two directions to take. You can either allow your surface to be singular, or you must allow it to have higher Picard rank. So let me discuss these two possible directions. So the first case is the case of a singular quartic surface. So let me take S, a general quartic surface. Let's take it with one singular point P. So I will assume, if I assume that the point P has coordinates 1, 0, 0, 0, then my quartic will have this expression here. And then in this case, because it is singular, I should not really look at the automorphism group of S, but I should actually look at the birational group of S. And if I take it to be general, then it's not difficult to see that the birational group of S is isomorphic to Z2. So I always have a birational involution, which is given by, if I take the singular point and I project from that point, this gives me, because it is a singular point, it's a double point, then it will induce a 2-to-1 map to P2. And then I take it the involution associated to this 2-to-1 map. So this is exactly this tau here. And if I take this A, B, and C general, this is going to be the unique non-trivial birational involution, birational self-map of S. And then in this case, using this theory of this volume preserved inversion of the Sarkisian program, we proved that, again, in this case, we have this exact sequence here, so that the decomposition group surjects into the birational group of S, and this is actually splitting. And also, we describe completely, I have to say explicitly, this inertia group. We write down all the birational maps in this inertia group, and in fact, this inertia group is what we call a form of GM over the function field in two variables. So this is the function field of P2. So a form of GM is just it's an algebraic group over this field, such that over the algebraic closure, it just becomes GM. So let me just give you explicitly at least one example of an element in this decomposition group. So if you take this Cremona transformation, you can check that this is in fact an involution, birational involution of P3, and you can check that it preserves the quartic surface and it restricts to this non-trivial involution tau. So this takes care of the case of say the general quartic surface. So, and when I say general here, I mean that again it has only one singular point of type A1, and it has a Picard group. The Picard group is generated by the restriction of a hyperplane class. Okay, so this is the first direction, and we studied a little bit more more singular quartic surfaces, and I don't want to state the result, but philosophically, the more singular your quartic surface is the more rational maps, the more complicated the birational geometry becomes. But now I want to consider the other direction, which is the case of a smooth quartic surface with higher Picard rank. So now I allow my surface to have Picard rank at least 2. So we will consider only the case of Picard rank 2. So I take a general smooth quartic surface with Picard rank 2. So in this case, the Picard group I can take a hyperplane class as one of the generators, and I complete it to a basis. And then with respect to this basis, the intersection form on S can be written by a matrix of this form. And one important invariant for our study is the discriminant of the quartic surface. So I can define it to be minus the determinant of such a matrix Q. So this will not depend on the basis. And so this discriminant, it says a lot about the geometry of the surface. So for instance, if you want to check if this surface S has a curve of certain degree and certain genus, you give me a genus and a degree, and you want to check whether there is a curve of genus G and degree D on S, well, then I just have to solve some system of equations that, it's given by this surface, and, it's often encoded, as we'll see, it's often encoded in R. So, for instance, in this case, and then what we show is the following. So this is with Paiva and Zikas. What we prove is that if this discriminant is either greater than 57 or it is 52, then the decomposition group is trivial, as in the Picard rank 1 case. I should say here that, for instance, the automorphism for a general quartic surface, the automorphism group only depends on this discriminant. And then for the other cases, what we prove is that if the discriminant is less or equal than 57 and it's different than 52, then again we have the decomposition group surjects onto the automorphism group. And in fact, this map here is splitting. And as I said, the automorphism group depends on the discriminant. And so this is the partition of the set of possible discriminants that lie in this set here. And then here I give you what is the automorphism group in each case. And in all of these cases, we can prove that every non-trivial, every automorphism is induced by a Cremona transformation. So let's see how much time okay, so I have some, can I use so I want to give you a sketch of the proof of this theorem. Maybe I'll do this in the blackboard. So again, as we were saying, I'm assuming that my discriminant is less or equal than 57, and it is different than 52. So let me give you an idea of the proof. So we suppose that there is an element in the decomposition group of P3, comma S. So this means that I have, and as we saw in this case, this is the same thing as the group of volume-preserving maps of this pair. So by the volume-preserving version of the Sarkisov program, I can decompose this map. So let's assume that this is non-trivial. So assume that this is a non-regular, say non-regular. So if I have this map, I can decompose it as I can write it, factorize it as a composition of volume-preserving links. So what I want to do is I want to look at what happens at this first link. So this, as before, this first link must start with some the blow up of a curve contained in X. So this first link starts with, let me call X, the blow up of a curve contained in S. So C is a curve contained on my quartic surface. Now, the first thing that we have seen, so exactly as in the first proof that I gave you, some facts that we prove is that the C is not a complete intersection of S with another surface. And also, something easy to see is that the degree, let me call this the degree in genus, let me call the D, call it the GD, for the genus and the degree of the curve. So first of all, C is not a complete intersection, and again, something easy to show is that this is a very general fact for any Sarkisian of decomposition. The degree of the curve must be less than 16. So this we always have, and moreover, in this case, what we show is that. So let me remind you how the link works. So we have P3. We blow up the curve. Then here we may have to do some small modifications, flips, flops, or anti-flips. Then we get to some other threefold here. And then maybe here, for instance, we can have, say, either a divisorial contraction or a more fiber space. But now, what we show is that this, in this case here, X, and this is, again, it uses the properties of the quartic surface here. So this map, that we cannot have anti-flips in X. So X does not admit anti-flips. So an anti-flip would be the contraction of a curve that has a negative intersection with minus k. So this curve would be contained in S. It would be a rational curve contained in S. But again, I'm using the fact that S has Picard rank 2, and then if you analyze the Picard lattice, you see that there is no room to have a curve that is blown up with these properties and a rational curve that would be contracted by the flipping contraction. So you cannot have anti-flips. So what this tells you is that this variety X is what we call weak funnel. So that means that the anti-canonical is nif and big. And then, but this setting has been studied by Blanc-Lamy. So Blanc-Lamy have a classification of weak funnels that are obtained as blow up of P3 along a curve. So Blanc-Lamy classify all possible pairs, genus, degree in this case, and then what you have to check is that here you have a finite set of finitely many possibilities for the discriminant, and for none of them you get a Blanc-Lamy curve. So then you just check that none of these Blanc-Lamy curves can be contained in a quartic surface with Picard rank 2 with this discriminant. And so this is what gives us the first part of the theorem. So this says that if the rank is either 52 or bigger than 57, then then you cannot have this. Sorry, maybe as I said it opposite here. What you show is that if you have such a curve C, maybe let me write this carefully. So if you so here there is a list. Maybe there is a few dozens of curves in the Blanc-Lamy list, and then if your surface C contains such a curve, then you have a sublattice Z plus ZH plus ZC contained in the Picard group of S. And now that means that this discriminant here of this sublattice must be divisible by the discriminant of your Picard lattice. And then you just compute the discriminant for all the curves in the Blanc-Lamy list, and then you check that the only ones that can contain such curves are the ones that satisfy this condition. So let me just keep track of the time. So I only have 5 minutes, right? So let me just explain briefly now. So this gives the first part of the result. So when it says that gives the restriction on the discriminant for you to possibly realize all the automorphism as a Cremona transformation. And now let me explain how you actually prove that in all those cases, all the automorphisms are induced by Cremona transformation. So let me just give you one example, which is the example where the discriminant is 56. So in this case, the Picard lattice is this one here. And in this case, the Picard, the automorphism group of S is Z2 free product with Z2. This can be read off from the lattice, that the automorphism group of this is this one, and even more. So let me take some generators sigma tau for this map. We can write precisely what are how these generators act on the Picard lattice. So they act by, say, this matrices here, and tau. And so what we have to do is we have to construct Cremona transformations that induce those true automorphisms. And again, what we do, we will use, we know that they would have some decomposition as a case of decomposition like this. So what we do is we actually, let's construct them by hand. So for instance, in this case here, you can take a curve, from the Blanc-Lamy list, this surface contains a curve of type genus degree equals to 2, 8. And then this, as I said, Blanc-Lamy, not only they classified the possible pairs genus degree, but they also describe each of the links that are obtained by blowing up these curves. And in this case, the link is something very nice. So you blow up the curve C, then you have to do a flop here, and then this gives you a birational involution of P3. So this link is very well understood. In fact, here you they factor through. You have a double cover of P through, and this is so this gives actually an involution. So this is this map. This is a 2-to-1 map to P3, and that preserves all this is the anti-canonical morphism of X. So this link is very well understood, and in fact, it restricts. If I restrict to S, this gives me precisely the my map, say one of them, sigma. And then to get the other one, what I have to do is, instead of taking this C, I take a C prime that is linear equivalent to 4h minus C. This is, again, a curve of type 2-8. And if I do the same, consider the link, then I will give me some phi prime, whose restriction to S is precisely the other generator. And so in this way, I can I can realize the two generators as restrictions of Cremona transformations. And so we actually do this to all the other cases. So maybe can we just, let me just go back to the slide and just to, sorry? Oh, it's okay, I don't need if it is not there, it's okay. Se no está ahí, está bien, no hay, No, no hay problema. Okay, I just wanted to show you the theorem again, to show them the list, but just to say that in all of those cases, again, we can just write down explicitly what are the generators of the automorphism group, and then using the Sarkisov links, sometimes not just one, but taking a composition of two links, we can generate them. Oh, okay. So let me, thank you, gracias. On. Oh, no, no. Okay, just to go to the last, it's just to state to have the theorem stated again. So okay, so in all these cases here, when I have the generators as involutions, I do exactly as I did here to realize them as Cremona transformations by choosing a suitable curve in the Blanc-Lamy curve, in the Blanc-Lamy list. And for these ones, things are a little bit more complicated. I have to take a composition of two links of that form, but again, I can realize the generator. So, okay, sorry, this is what I wanted to tell you. So, gracias. Okay. La pizarra. Sí. Yes. I can yes, I can take any curve in the linear system. You can take any curve in the linear, if you take any curve of this type, it will induce that involution. So this is what this is saying is that the inertia group is huge. So we have not yet started to investigate the inertia group, but exactly as you say here, you could take any curve in the linear system and it will induce this, it will be a different birational involution of P3 if I take different curves, but when I restrict it to the surface S, it will give me always the same involution. So the inertia group is huge. And we haven't yet studied the inertia group in this case. Yes. I asked this to Jean today. This when I was searching, I saw his yes. Okay, so you really? Oh, okay. Oh, very nice, very nice. no, this goes to infinity. So if you could think you can have arbitrarily large discriminant. I don't have the matrix here, but the matrix, if you take any matrix of this form, 4, B, B to C. So if you take any matrix of this form, this will give you a K3 surface. So, and then you can choose B and C as you wish. So the discrete, you can construct surfaces with arbitrarily large discriminant. So thank you for asking this, because this is what I wanted to say in the end, is that what this is telling us is that the answer to Ghizzatulin's question should be almost never, except in the trivial cases. So already in the Picard 2 cases, most of the quartics will have higher discriminant, and so what this theorem is saying is that you cannot realize its automorphism. And then the automorphism group, again, you can take them to be the 4 groups, and then yes. So this sorry. So this will so the dimension of the so that you have always have moduli space of a quart. If you fix the Picard lattice, then the dimension of some cases of some say K3 surface, the moduli space of K3 surfaces whose Picard lattice contains this given lattice is always 20 minus 20. Let me try to get this right. 20 minus rho. So in this case here, it will be 18-dimensional. You have an 18-dimensional family of quartics with this Picard lattice, or whose Picard group contains this Picard lattice. So I have not. So we have not looked at the higher Picard rank, but the example. I think I would guess that it's a similar story. So the example that Ogizzo constructed was probably a very special example where all so his case, in his example, the Picard rank, it was 3, and the automorphism group was Z2, Z2. But in this case, he constructed in such a way that these involutions were associated to some elliptic fibrations, and then he used this to realize them as Cremona transformations. But those were, again, was very carefully chosen Picard lattice. I would guess that if you take a general Picard lattice, it will, again, it will be as in the, but we haven't checked. No, I think it's huge. It's huge. It's yeah. I would say it's huge in this cases. For instance, exactly in this case here, you can take the linear system of if you take any curve here in the this linear in this linear system, and I think the linear system is always will have dimension 3, I guess, the G plus 1. So any curve here will induce the same map. So the inertial group is huge in this case. That's a good question. Okay, my guess would be yes, and my guess is that probably these techniques could could help you prove this. Because, for instance, in this case here, the first link must be given by the blow up of such curve, and this has a certain degree. And so I would guess that, but okay, but I don't know.
Other questions? Not, let's thank Carolina and all the speakers.
And well, since I'm the last speaker, I would like that we also give applause to the organizer of the session. Ah, sí.
Esta es la de la foto de arriba.
¿Cómo?
Esta es la de la foto de arriba.